Hello, I'm Andrew Nenka. Thank you for joining me for this 2023 ISMRM e-poster titled GRAPPA Interpolation with Unity Acceleration Enhances Signal-to-Noise Ratio in Fully Sampled Acquisitions. I'd like to offer special recognition to Kyle Johnson and Jason Stobris from the Department of Biophysics at the Medical College of Wisconsin, who acquired the preclinical data shown in this presentation. I have no conflicts to declare with respect to the content of this presentation. It is well known that radiofrequency coils with spatially varying receive fields impart a correlation between neighboring K-space observations. In short, the K-space observations from a coil are the convolution of the Fourier transform of the coil sensitivity profile with the imaged sample's Fourier encoded image. As such, each K-space sample for a coil can be modeled as a weighted average of its neighboring samples if the coil profiles vary gradually in space. This relationship is well exploited with the GRAPPA technique. Here we consider the case of applying a GRAPPA algorithm to estimate K-space observations even when K-space subsampling is not performed. As this yields an effective averaging of observations, the application of the GRAPPA algorithm to unaccelerated acquisitions should yield an improvement to the reconstructed image's signal-to-noise ratio. In this work, we acquired data on both 3T and 9.4T systems. The 3T system was a GE Healthcare Cigna Premier with 48-channel head coil, and the 9.4T system was a Bruker BioSpec 9420 with locally developed single-channel receive coil. Further details of the acquisitions are in the first two columns of the slide. Reconstruction in all cases was performed by reading the raw K-space data from the EPI acquisitions into Python. Datasets were reconstructed with standard Fourier reconstruction and, for the experimental case, with an 11 by 11 by number of coils GRAPPA kernel fit with Tikhonov regularization over the totality of K-space from one repetition. To ensure matching point spread functions in the compared datasets, K-space observations in the standard and R=1 GRAPPA reconstructed datasets were truncated to only the points with sufficient support to apply the GRAPPA kernel. The temporal signal-to-noise ratio was computed for each reconstructed dataset, which was then masked to regions of signal intensity above threshold in the traditionally reconstructed image. A point-wise difference in TSNR between GRAPPA R=1 and standard reconstructed datasets were compared with a non-parametric Wilcoxon U-test. Here are representative coil images from the human, phantom, and preclinical acquisitions. The GRAPPA inferred K-space shows a more smooth variation as would be expected due to the convolution of K-space with the Fourier transform of the coil sensitivity map. Differences in noise profile between the single coil reconstructed images is clearly apparent in each case, with reduced noise in the inferred images. Improvements of 1 to 6% were observed in the reconstructed time series signal-to-noise ratio. In each case, the improved TSNR was statistically significant. Higher SNR improvements were observed in the 48-channel coil, likely a result of the improved modeling associated with having more coils for kernel estimation. It is important to note that this TSNR improvement was beyond the SNR improvement that one can achieve with a sensitivity-based optimal coil combination. As resolution increases and applications for low-field imaging grow, techniques to improve signal-to-noise ratio are helpful. In this work, we used local correlations between neighboring observations in K-space arising from spatially varying coil sensitivities to model each K-space observation as a weighted sum of its neighboring observations. Thus, using the formulation of GRAPPA with a unity acceleration factor, full K-space can be used to infer a noise-reduced K-space. This can yield improvements in temporal signal-to-noise ratio of a few percent. This technique can be applicable to signal-starved acquisitions like non-proton or preclinical surface coil imaging, or other clinical applications which do not have sufficient signal-to-noise ratio to justify the use of parallel imaging. In conclusion, we showed here that applying the algorithm of GRAPPA on unaccelerated acquisitions can yield an improvement in signal-to-noise ratio on the order of 1 to 6%. Thank you for watching my presentation.